Hello class, today we're going to be talking about lesson 22, which is on logarithmic and exponential equations. So essentially solving equations that have exponentials and logs in them. Alright, so let's get right to it and start looking at some examples. I think it's usually easier to just see how to do it versus, talking about it first. But let's take a look at some examples. All right, we're going to first turn our attention to exponential equations. So that's when we have equations of this type. Say we have 5 to the 2x is equal to, say, 25. Okay. In examples like this, all right, so where we have x's in our powers, in our exponents. There are two ways we can go about it. One, in this case, we have a sort of a nice situation where I have 5 to the 2x, and 125 I can actually write as 5 cubed. Yeah, so I have 5 to the 2x is equal to 5 cubed. And so, since these are 1 to 1, all right, if I have 5 to something is equal to 5 to the third, that must mean that something is equal to 3. All right, if 5 to some power is equal to 5 to some other power, those powers must be equal. So then I can just divide by 2 and get x is equal to 3/2. Okay, and in this situation, MyLabs+ is going to do the whole solution set for a lot of these. So you would say the solution set is this 3/2. So here's another situation where we can use this idea. I have 7 to some power is equal to the square root of 7. Well, if we remember that the square root of 7 is 7 to the 1/2, what we essentially have is 7 to some power is equal to 7 to some other power. Right? So if 7 to some power is equal to 7 to 1/2, those powers have to be equal for this equation to hold. So you get that x minus 3 over 2 is equal to 1/2. Okay? And we can solve this like we've been doing before with our linear equations. I can multiply everything by 2, because that will get rid of our denominators. So I get x minus 3 is equal to 1. So moving the 3 over, I now get x is equal to 4. And there we go. Okay, the solution set is 4. Okay? So if you can get things down to being the power, base to some power with x is equal to base to some number, then you can solve by just matching these equal to each other. Okay, because if you can get the bases to match, then the powers must also match. Okay, so in other words, if the powers match, or let me put it actually instead say this, if the bases match, then the powers must match as well. So then the powers must also match. Okay. All right, what happens if that's not the case? Let's say we don't have something that nice. So for example, say we had something like this. 2 to the x is equal to 3. Okay, so this is your general exponential equation. And equations of this type, how we go about solving them is we're going to use the property of logs that allow us to take powers outside and move them down as multiplication. So what we're going to do is we're going to take the natural log of both sides. And the reason we use natural log is partly because it's on our calculator, partly because the natural log is our most important log. We could also use log base 10 if we wanted to, but MyLabs Plus even specifies to use natural logs for everything. Okay, so when you take natural log of both sides, you'll take the natural log of 2x, and you'll say that's equal to the natural log of 3. Okay. Then you will use that property that lets you take that x power, outside. So we're going to take that power x outside and now have x times the natural log of 2, which is equal to the natural log of 3. Okay. Now to solve, we're almost done. Okay, all we need to do is I have x times natural log of 2. Well, this is just some constant. Off the top of my head, I'm not sure what it is, okay? But I know it's just a constant. Okay, so all I'm going to do to solve for x is just divide both sides by natural log of 2. Okay, so that these cancel here. I get x is equal to natural log of 3 over natural log 2. Okay. So MyLabs Plus is actually going to ask you to write your solution set in terms of natural logs to start with. So it will say the solution set is, you would just say ln3 in this case over ln2. Okay, but also it's going to ask you for a decimal place or a decimal expansion. So we would plug ln3 over ln2, if you can see that. So ln3 divided by ln2, which is 1.5849 blah blah blah, and let's round this to 2 decimal places, so 1.58, and there we go. There's our answer. Okay, so in general, to solve a general exponential function, you take natural log of both sides. Okay, and actually so to solve equations with x's in the exponent, also called exponential equations, okay, you're going to start by isolating the weird thing, right? That's always our first step. So start by isolating the weird thing. In this case, that will be your b to the x. Then take natural log of both sides. Okay, and that is how we solve exponential equations, general exponential equations. So let's look at a couple more examples, because they aren't all as simple as just 2x is equal to 3. But if I want to check, because this is like a log, right? 2 to what power is equal to 3? If I take 2 and I raise it to the answer, like I talked about last time, we get 3. Okay, so that's the power we need to raise 2 to get 3 out. All right, let's look at another example. Okay, so let's say we have this equation. 4e to the 9x is equal to 828. So we're going to start by isolating the weird thing. We're going to isolate the e to the stuff, right? E to the 9x. So we do that by dividing both sides by 4. We want to get rid of that 4 out front. Okay, so what this gives us is that e to the 9x is equal to 828 divided by 4, which turns out to be 207. Okay. now that we've isolated this e to the stuff, so it doesn't just have to be isn't always just to the x. It could be to the 9x, it could be to the 10x, it could be to any weird thing like this. We're going to now take ln of both sides. Okay. So we'll get ln of e to the 9x is equal to ln of 207. Okay. Now here, ln of e to the 9x, remember this is going to simplify because this asks, remember what the natural log asks, this asks e to what power is equal to e to the 9x. Well, that question mark better be 9x. So ln and e, whenever they touch, they cancel. So this actually just comes out to be 9x is equal to ln of 207. So you can actually just also think of this, if you have ln of e to the 9x, you can also move the 9x out to get down to 9x ln e, and ln e, as we've talked about before, is 1. So either way, we get down to 9x over here. So we have 9x is equal to ln of 207. To solve for x there at the end, we're just going to divide by 9. So divide both sides by 9. 9's cancel, and so I get x is equal to the natural log of 207 all over 9. I like to keep my parentheses there, but you'll see a lot of times the book and MyLabs Plus and all that, they'll actually just say ln 207 over 9. Okay, and that would be my solution set. And then if I wanted to find what that was on the calculator, if I can get it so you can see what I'm typing, I would do ln 207, close my parentheses, divided by 9, and we get about 0.9 or 0.59 when we round to, say, 2 decimal places. MyLabs Plus will actually tell you how many decimal places to round to if they're, picky about it, if they care. But there we go. Okay, so here's our x value. Okay, for this one, I have 2 plus, now, 9 all to the x minus 2 is equal to 306. Okay. So like before, first thing we want to do is isolate the weird thing, right? This 9 to the x minus 2, we want to isolate that to begin with. Okay, so to do that, we'll actually move this 2 over. So keep in mind, this is not 2 plus 9 all, only the 9's being raised to that. So we can healthily move this over by subtracting by the 2. Okay, so now I have 9 to the x minus 2. Notice I put parentheses here just to really drive home the fact that I am only raising 9 to the x minus 2. And the entire x minus 2. So it's not 9 to the x minus 2 on the outside. It's actually, all this is in the exponent. Okay, so then we get 304. Okay, now that we're here, now we're going to take ln of both sides. All right, so I'll get ln of 9 to the x minus 2 is equal to ln of 304. So in this case, the ln does not cancel with the base this time. Okay, last time we had e, so it did. This time, what we'll do instead is move out that x minus 2. Okay, so that x minus 2 comes out to give us an x minus 2 times the natural log of 9 is equal to the natural log of 304. Okay? Now here's the trick to this type of equation. Before I had an x, now I have an x minus 2. That's actually okay. We'll just divide by the natural log of 9 on both sides. Because because that'll cancel here. Then I'll get an x minus 2 is equal to a natural log of 304 all over a natural log of 9. Okay? So, now if I want to solve for x, get it all by itself, I'm going to add 2 to both sides. And I can just do that here and get that x is equal to the natural log of 304 all over the natural log of 9 plus 2. So this is your answer in what is called exact form. Okay, this is the exact solution. If I want to find the decimal approximation, we will just plug this in as we see it. Okay, so natural log 304 divided by natural log of 9 plus 2. Okay, notice I closed all my parentheses. See that? I closed it. I was very careful about how I wrote this. And there we go. We get about 0.46. Okay, and that's if we're rounding to 2 decimal places. All right, let's look at another example. Although before we do that, let me show you here. This was the answer we got for our x. So let me put it back into this form of the equation if it would focus. This form of the equation, the 9 to the x minus 2, and see if we get 3 over 4. So 9 raised to, and I'm just going to put answer here because that's what I got for my answer, minus 2, and we get 304. Okay, so that's, well, we checked it, we got it. Okay, so this taking ln on both sides actually works out for us. Okay, this equation's a little weird. This example is a little weird. We have exponentials on both sides. Okay, so what we're going to do is, there's no, I mean, there are ways we could go about doing this, but the best way is to just take, because the isolating is not really going to help us here. So we'll just try take ln on both sides and see what we get. Okay, and so I'll get ln of 2 to the 4x plus 1 is equal to ln of 3 to the x minus 3. Okay, and then we can actually bring both of these things out. Okay, and get a 4x plus 1 times ln of 2 is equal to x minus 3 times ln of 3. Okay. Now remember what we did in that one of those first equations we looked at. What we said when we just had an x, we said, oh, well, we have ln2 here. I don't know what that is off the top of my head, but I do know that it is just a constant. And I know that this is a constant. Okay? So usually, if this were just a 2 or a 3, all we would do is distribute these values and move our x's over to one side, everything else to the other. Okay, we'll do the same thing. We'll distribute these constants across so that I get 4x ln2, okay, plus 1 times ln2 is equal to, and we'll do the same thing here, x ln3 minus 3 ln3. Okay. All right, now I'll move all my x's to one side, everything else to the other. So now we'll move x's to one side, everything else to the other. Right, so I'll move this x ln 3 over to this side. So I'll get 4x ln 2 minus x ln 3. And then I'll move this ln 2 over to get minus ln 2 minus 3 ln 3. All right, it's kind of complicated, but remember, these are just numbers. I don't know what they are, this ln 2 and ln 3, until I plug them in my calculator, but they're just numbers. Okay, we don't have to, worry too much about it. And now here, I'm just going to factor out my x. So in this case, on this side, we'll factor out x. All right, so I'll get x factored out, and I'll be left with a 4 ln 2, and then here just a minus ln 3. And you can kind of start to see why the book and everybody starts to not write these parentheses out, because they start to kind of get a little cluttered with a lot of parentheses rolling around. But do be careful. Without parentheses, all you're assuming is that only the numbers are getting plugged in. And now, once again, this is just some number, this 4 ln 2 minus ln 3, so I will just divide both sides by this entire thing. Okay, which will cancel, and so finally my x ends up equaling the fraction negative ln 2 minus 3 ln 3. Let me put my parentheses back in, all over 4 ln 2 minus ln 3. And I wanted to look at this example because it's one of the most difficult ones like this. It involves, distributing and moving things around and dividing. But as long as you're careful and remember that these ln of things are just constants, you'll treat them just like normal numbers, like 2 or 3. They're just a little more cluttered. You can still get down to your final answer, which, let's be very careful how we do this. We'll do open parentheses negative ln of 2 minus 3 times ln 3. Right, so there's our entire numerator. Then I'll put the entire denominator in parentheses too. You need to be very careful about that. And then I'll close my parentheses for that. So notice the entire numerator and entire denominator are in parentheses, and there we go. We got, in this case, negative 2.38 if we rounded to 2 decimal places. Okay, so that's one of the trickiest ones you're likely to see. Let's do another exponential equation. This one will also be kind of a tricky one until you see what the trick is. Okay, say we had this equation here. 7 to the 2x plus 7x minus 30 is equal to 0. Okay. At the moment, it may not look like we can do anything to isolate these. But here's the trick for this one. Okay? If you let, let's say, u be equal to 7 to the x, and then I look at u squared, that would be 7 to the x all squared. And what do you do when you have something to a power, you multiply those exponents. So this equation, 7 to the 2x plus 7 to the x minus 30, actually becomes, using this translation, u squared plus u minus 30 is equal to 0. Okay? And now this is just a quadratic. Now we want factors negative 30, that sum up to equal this middle term, 1. Okay? So negative 30, so one's got to be positive, one's got to be negative. So negative 30 is, of course, 3 and a 10, so, and then that's 5 and 2. So my options are, I think I have it, it's 6 and, 6 and negative 5. Right, 6 times negative 5 will give me negative 30. 6 minus 5 will give me 1. So this actually factors to be u plus 6 times u minus 5. Okay? So, we get that u is equal to negative 6, or u is equal to 5. Alright, so be on the lookout for this pattern. Remember, we did this back when we were talking about solving different types of equations. We were always on the lookout for this pattern because we could factor it. Because now we can actually change our u's back to these x to the 7ths. Or other way around, 7 to the x's. Alright, so I get 7 to the x is equal to negative 6, or 7 to the x is equal to 5. So we can solve these two equations individually now. Well, this one we need to worry about, because remember, if I were to take ln of both sides, that's usually our first step. We run into problems here because this is undefined. Right? We're not allowed to plug negative values into natural log. Okay, natural log, the domain, is all x is greater than, well, all values greater than 0. Right? We can't plug in 0, and we can't plug in negative values. You can also think of this as, well, is there anything I could plug into this that would give me a negative out? So let's try it. If I put negative values in the power of 7, or sorry, if I put positive values, I get positive values out. So like 7 to the 1 is 7, 7 to the 20 is a really large positive number. 7 to the pi, for example, is also a large positive number. 7 to the 0 is 1. And then if I put negative values in, I also get positive values. So if I put negative 20 in, I still get positive values. Okay? So there's actually no exponent I could put in to get 7 to the x to be a negative 6. Okay? So this has no solution. That's an extraneous solution. While this one we can actually deal with, because when we take the natural log of both sides, we get the natural log of 7x is equal to the natural log of 5. Moving that x outside, we'll get x times the natural log of 7 is equal to the natural log of 5. And there we go. Now we can just divide both sides by this ln 7. To get that x is equal to the natural log of 5 over the natural log of 7. Okay, which comes out to be, when you plug it in your calculator, I won't go to the trouble this time, but of actually showing you, but it comes out to be about 0.83 when you do it. Okay, so there are exponential equations. Now let's turn our attention to log equations and see what happens there. Okay, so for example, let's say I have log base 2 of x is equal to 3. Well, the trick of the log equation is actually not even as complicated as the exponential equation. We just rewrite this as an exponential. Okay, so here's my base, right? The base is equal to 2. So remember, it's always base to a power is equal to the value. So the base here is 2. The power, remember the power is on the other side, which is 3. And is equal to the value, which is here, x. Oh, so x is just equal to 2 cubed, which is 8. And there we go, 8. Okay, if we plug it back into the solution, log base 2 of 8 equals 3. Well, is that true? Well, let's see. This is asking 2 to what power is equal to 8? That answers 3. So we get 3 is equal to 3, and there we go. Okay. So with log equations, it really is just down to making sure you rewrite it as an exponential. And usually it just kind of, goes from there. Now, of course, you can complicate it a little bit by maybe giving it an ln or giving it an x plus 8 instead of just an x. But it still works in the same way. Remember, we want base to power is equal to the value. Okay, so the base for ln is e. The power is on the other side, 2. And this is equal to x plus 8. And to solve for x, I'm just going to subtract 8 on both sides. Now, that's not necessarily going to be a nice number. I'll flip things around. So this will be e squared minus 8. So that doesn't come out to be a nice number necessarily. But we could still figure out what that is. Going to our calculator, we'll do e squared, remember to close your parentheses there, minus 8, and that comes out to be about negative 0.61 if you round to a single decimal point, or to 2 decimal places. Alright, so there you go, and we could actually test that out like we did before, ln of x plus 8. So if I do ln of our answer plus 8, I should get 2. Okay, let's look at another one. Okay, so for this one, again, we always want to isolate the law. So here, with this 9 plus 24 log base 2, 2x plus 1 is equal to 21, we're going to start by isolating the log. So I'm going to move that 9 over, okay, and moving that 9 over, subtracting both sides, will give me the 24 log base 2, 2x plus 1 is equal to 12. Then I'm going to divide both sides by this 24. Right, so that's the trick here, is to make sure you get the log stuff all by itself on one side, everything else on the other. Now we're not messing with the inside, just the numbers around it. All right, 12 divided by 24, that will end up being 1/2. Okay, so now we're going to rewrite this expression here using an exponential. So let's rewrite using an exponential. Okay, so this one's going to be kind of messy, but we should be able to get it. Our base is 2, so remember, it's always base to power equals value. Okay, so the base here is 2. The power comes from the other side, which is 1/2, and is equal to the value, which is here on the inside, which is the 2x plus 1. So 2 to the 1/2, that's the square root of 2. And the rest of this is just linear. So we can solve this like normal. I can subtract 1 on both sides. Okay. So I'll have the square root of 2 minus 1 is equal to 2x. And then we'll just divide by 2 on both sides. Okay? So we'll get square root of 2 minus 1 all over 2 is equal to x. And there we go. Okay, so not the nicest thing in the world, but if I plug this in, I'll do the square root of 2 minus 1 all over 2. I get this. And then if I check that back in my original form of the equation, we could do this version of it. Remember, we don't really have a log base 2, but we could rewrite this as log of 2x plus 1 over log of 2 if we want to actually check this. So log of 2 times the answer plus 1 divided by log of 2 gives me 0.5. And that's what we have there. Alright, let's look at another example. Okay, say we have an equation like this. Log base 5 of x plus 16 plus log base 5 of x minus 8 is equal to 2. So what we're dealing with here is a situation with two logs of the same base. Okay? So remember, our first step is always to isolate the log. Okay? So in this case, that actually means getting a log of one expression. So if possible, one log. Okay? So we're going to use that property we talked about in the last lesson, where when we are adding two logs, we can actually bring them together using multiplication. So I can get log base 5 of this guy, this x plus 16, times this guy, this x minus 8, and that whole thing is equal to 2. Okay? And now that I have this as a single log, now we can rewrite as an exponential. Okay? So to do that, our base is 5. I'll go ahead and change the equal signs already, but it doesn't matter. But it's 5 to some power, the 2. Right? 5. The base is 5. The power is 2, and the value is this thing here, this x plus 16 times this x minus 8. Okay? And there we go. We get x plus 16 times x minus 8 is equal to 5 squared. So this side is going to be 25. This side we will actually multiply out, FOIL that out. So we'll get x squared, okay, minus 8x. So I distributed the first, the outside, the inside, plus 16x. And plus 16 times negative 8. So 16 times negative 8 will be minus 128. Alright. So this equation simplifies down to be x squared minus 8x plus 16x, that will be plus an 8x. And then what I'm going to do is bring that 25 over. So I'll go ahead and subtract the 25 in the same step that I'm combining these like terms. So what we get is now this equation here, this x squared plus 8x minus 153. Ugh. Okay, so this does not look very pleasant, but it might factor. And the reason we can try and factor this, or we could use the quadratic formula, but I think it might factor. Let's see. Okay, I want factors of negative 153 that sum up to 8. So 153, if I divide that by 9, I get 9 and 17. So let's try 17 and negative 9, because 17 times negative 9 will give me negative 153, and then 17 minus 9 will give me 8. So that's it. X plus 17, x minus 9. Okay. Alright, so that gives us x is either equal to negative 17 or x is equal to 9. Okay, here's the thing with logarithmic equations. Most of the ones we've looked at so far have come out to be nice, right? We've gotten one solution, and those solutions have worked when we plug things back in. That's not going to be the case here. Okay? When we plug in 9, we should get everything working out, because we'd get 9 plus 16 plus log base 5 of 9 minus 8. So we'd get log base 5. So actually, let me plug the value back in. Let me just do it. If I want to plug 9 in. So I'll do that here in red. Plugging in 9, we get log base 5. 9 plus 16 would be 25. Plus log base 5 of 9 minus 8 would be 1. So you get log base 5 of 25. That would be 2. Log base 5 of 1 would be 0, which is 2. So it actually works out. Okay, and remember that's because 5 to what power gives us 25? 2. 5 to what power gives us 1? 0. On the other hand, this is going to cause us problems. X equals negative 17 is problematic because log base 5 of negative 17 plus 16, that's our first term, is log base 5 of negative 1. And this is undefined because we can't plug negative numbers into logs. Okay? So whatever solutions we get, these things have to be positive when we plug them in. Whatever we're plugging them into need to be positive. So this x equals 17 is an extraneous solution. We need to throw it away. So the solution set, I'll just do it over here. The solution set here (9). And that's that. So just be sure when you do these, make sure you check. If you start with a logarithmic equation, your solutions can't cause the input to be negative. Okay, so in a case like this, where we have 2 logs, what I'm going to do is I have 1 log on one side, 1 log on the other side, but this one, log base 4 of 16, I can actually evaluate that, right? 4 to what power equals 16? That's 2. So this thing comes out to be 2. So what I have is 2 log base 4 of x plus 14 is equal to 2 plus 2. So we get 4 on this side. And now we can isolate the log by dividing by 2. And so now I have log base 4 of x plus 14 is equal to 2. And now we can just rewrite as an exponential. Right, so my base is 4, my power is 2, my value is x plus 14. So now we just get down to that this equation. 16 is equal to x plus 14. And it's very, we just subtract 14. Whoops, didn't do that. We just subtract 14 on both sides to get that x is equal to 2, and there we go. Okay, so don't go through the really tough process if you can actually evaluate one of these logs. Okay, what happens if we have all logs and none of them can be evaluated? So instead of isolating, what we're going to do is try and get it so we have logs on both sides. So if we can't isolate, okay, what we'll do is get logs on both sides. So what we'll do is we will use our product principle here, product property. So we will get, now we'll multiply these together. So log of x plus log of 12 I can bring together as log of x times 12. And now that I have a log of something is equal to a log of something else, those somethings must be equal. So it works just like with the powers. So like we had before, when we had b to the x was equal to b to some number, that meant that x was equal to that number. Okay, we have the same thing here. If I have log base b of x is equal to log base b of something else, those things on the inside have to be equal for that to work. Okay, so if two logs are equal to each other and they have the same base, the insides must be equal. So what we have here is that x plus 12 is equal to 12x. So we move the x over to get 12 is equal to 11x. Therefore, x is equal to 12 over 11. And there we go. Okay, so if we started with this equation, 2 log x is equal to log 4. Since I have 2 logs on either side and it's going to be hard to actually isolate them, what I'll do is just get it so I have 2 isolated logs on both sides. So I'll move that 2 up into the exponent to get log x squared is equal to log of 4. And then if log of x squared is equal to log of 4, that tells me that x squared must be equal to 4. So x is equal to plus or minus 2. Now, you got to be careful. Gotta be very, very careful. Here, in our original equation, so we're going to check the original equation. Which is 2 log x is equal to log 4. I can't plug in -2 into this. Don't go to this one. Go to this one. Plug in that into the original equation, and -2 is not going to work. So only +2 is the solution here. Okay, so the solution set Okay, that was a lot of examples of these things, and unfortunately I can't go through every single type you will ever see, but broadly speaking, this covers the general types of exponential and logarithmic equations that you'll run into. Okay, so from here you should be able to at least take a crack at all the homework, but as always, if you have any questions, please don't hesitate to let me know. Catch you all on the next one. So, cheers.